Everybody's freaking out? Alright, so 3 things we talked about yesterday. Give me one of them. Kendall's group. One main concept we talked about yesterday. Heat curve, right? Everybody draw a heat curve again for me? Okay, it's a staircase, not a curve. Okay. Another thing we talked about, Cole's table. Okay, so phase changes in general, right? So we learned about the states of matter, solid, liquid, gas, and all the phase changes that can occur between them. And then last thing, Kern's table. Cool curve and heat curve kind of relate to each other. So the other thing, somebody else at your table?
Like when we were doing things with the ion.
Okay, so that was like phase changes. We were looking to see how they were moving and their behavior and the phase changes that went with it. There was another diagram we drew. What was it called? We just haven't gone in depth about it, but you guys had it on your notes from yesterday. What's it called? What's the one with the Y thing in the middle? Phase diagram, right. So we have phase diagrams, we have heat curves, and we have all the state changes that we have to be able to interpret. Okay, so since we're dealing with phase changes, we have to talk about the fact that things can boil or evaporate or vaporize, things like that. So there's an application of vapor pressure or boiling, and that's a relationship between atmospheric pressure and the pressure of said vapor. So just so we're clear on what vapor pressure is, it's literally the pressure caused by a what? A vapor. What's not crazy, it's the pressure caused by vapor. And so we should know that pressure has a specific definition. It's collisions with like a container. So if I have a container like a soda bottle, and I have some gas, like carbon dioxide or something like that in the soda bottle, it's got some pressure to it. I can't squeeze and crush the soda bottle if it's closed. There's pressure on the inside stopping me from doing that. So there are some things that are in life more likely to cause pressure to vaporize, and that word right there, volatile, is the definition. And like that basically just means its behavior is likely to vaporize or likely to evaporate. So think of something that you open, like it's like encapsulated in like a bottle. Think of something you open, and you open it, and you immediately smell it. What? The tennis ball things. Those are just gases from the plastic part of the tennis ball. Something else? This table? You open it, you smell it, you're like, whoa, strong. Vinegar. Yeah, it's a great volatile substance. We can smell it from across the room. Something else up here? Okay, so the volatile substances from the chips actually are what's causing that to smell. Think of like if I brought in a box of donuts. Gosh, and they were warm. Gosh, you could just smell it, right? So there's a lot of things in life that are technically volatile. The reason they're volatile, though, is because they have enough kinetic energy to move from place A to place B. Hopefully, and of course, you would smell them at place B with your nose, because they would move to your nose, and your little nose receptors would catch them and say, you're smelling donuts. Okay, for liquids, from a liquid standpoint, only your surface is the place that vapors occur. You don't vaporize from the bottom of a liquid, you vaporize from the top of a liquid. All right, so here's a diagram of that. You have your surface, you're vaporizing to gas, and then you can also condense back down from gas to liquids. There's a cyclic relationship. If you heat them up, vapors begin to occur more and more and more. Heat them up, vaporization can occur more and more and more. Eventually, though, we'll get to the point where vaporization, this process will equal condensation, which is that process. So it is cyclic. What we should know, though, is that the actual temperature at which something boils, the temperature relationship, is actually related to the pressure of the atmosphere. So Bryce is going to be, Bryce, you're going to be the atmosphere. Come here. All right, so I will be the vapors. Okay, so I'm like the beaker, and my vapors are trying to form. They want to push. Okay, you be the atmosphere. You're just playing patty cake. That's it. Okay, so he's the atmosphere. He's pushing down, pushing. Okay, he's the atmosphere. He's pushing down. So the atmosphere is pushing all around us. And if I'm the vapor, I don't have enough energy to get past the atmosphere, am I going to vaporize? No, so I'm not going to boil. But until I have enough kinetic energy to push past the atmosphere, I'm not going to boil. So once I hit that point where I have enough kinetic energy to push past the atmosphere, I will then boil. So there's a specific temperature. Thank you, atmosphere. There's a specific temperature at which that will occur. Thank you, Bryce. Thank you. Free bird. All right, so at a specific temp. what's that temperature specifically at our atmospheric level for water? What's the temperature that water boils at our atmospheric temperature? I mean, our atmospheric pressure. Don't you say the F word. 100 degrees Celsius. Okay, so we're going to talk in Celsius. What is that in Kelvin?
Oh, that's 373.
373 Kelvin, because what's the difference between Celsius and Kelvin? 273 Kelvin. Okay, so that's basically the definition of boiling. When the atmospheric pressure equals the vapor pressure, definition of boiling point. All right, so we got here yesterday, yes? You guys can write down examples, so we're good to go. I thought I would show you guys this. There's a reason that we have, actually, if you ever look on a cake box or pasta, some instructions differ. If you're like in Denver or in North Carolina, the atmospheric pressure can deviate and it can cause differences in boiling points. So if I'm on a mountain, okay, if I'm starting down here, let's call this 1 atmosphere. Like this is our atmospheric pressure as in Kakalaki. Okay? If you climb a mountain, let's climb Mount Everest. Okay, what's going to happen to the atmospheric pressure up here? Okay, so is it going to increase or decrease? Decreasing, because here you have all this gas pushing down on us. There's a lot of atmospheric pressure here. Up here, let's give it a number for me. So you said it decreases in pressure. So what number should we be looking at? Something less than 1, right? So I'm going to say 0.5 atmospheres. Okay. So this diagram helps you draw it for yourself. In higher altitudes, the atmospheric pressure is lower because there's less gas above us pushing down. So if you're up here versus here, there's going to be a difference in boiling point because things will vaporize at different pressures. So basically, Bryce would be less strong on the top of the mountain, but he would be very strong down here. The atmospheric pressure would be stronger. So where would this boiling point be? If this boiling point of water is 100 degrees Celsius? Okay, 50 is really dramatic, but I think let's go with less than 100. Okay, so I don't know. Let's go to 70. So the reason this differs is because down here, this water's got to really crank up its kinetic energy to get past the atmospheric pressure. It's got really good kinetic energy to push above 1 atmosphere. Here, it doesn't have much to fight back on, so the temperature doesn't have to get quite as hot for it to vaporize at that point. So it's just going to have a lower temperature at which it should boil. So what we can see is across various locations, elevation is almost 9,000 meters. Water boils at about 70 degrees Celsius. I kind of guessed, so it's nice there. Sea level, water boils about 100. The Dead Sea, which has a elevation of negative 400 meters, so that would be like if I went to the mountains and then I kind of said, okay, let's go to the Dead Sea. What would be the atmospheric pressure down here? Say it again. 1 plus, right? So something higher than 1. So let's call it 1.5 atmospheres. And that down there would be requiring us to really heat up. If I were to boil water underwater, that would be the coolest thing I've probably done in my life because it's underwater. How does just boil water underwater? Anyway. So if you have higher atmospheric pressure, it should increase the temperature required for the kinetic energy to get to the point where it technically can boil. So that was just a cool diagram I want to show you is that. All right, so high altitudes, boiling point does what? Decreases because there's a lower atmospheric pressure at the highest points. Okay, so what's this thing called again? Phase diagram, because it shows the phases of matter. And what are the 2 axes? Pressure and on the bottom, temperature. You have a diagram of this from yesterday. I do specifically want to use this one in class today, so I'm going to give you a second to draw, sketch. There's only a couple of numbers here, so those numbers would be important to include as well, okay? So include this from or within your notes. I'm going to try to sketch it on the board as well. It does not have to be beautiful, so it needs to be functional. We're specifically interpreting off of this diagram. That's why I want you to have it on your paper. So the pressure's in kPa, so kilopascals, which is another unit of pressure. The temperature is in Celsius. And there are a couple points I also want you to label. A is way down here on the corner towards the Y and X intercept. B is at the trickle point. C is like way up here. D is over here at the critical point. I think that's it. Yeah. Okay, so noting the pressures in kilopascals and the temperatures in Celsius, that's two axes we should understand. This is basically telling us if I change, or if I have a certain pressure and a certain temperature, what phase of matter will exist for this substance. So let's call this substance, I think this one's for water, based on what it looks like. So it's basically saying, at what pressure and temperature can I modify the water particles to be solid, to liquid, to gas? I can cause all these phase changes to occur. So the definition of normal it does have a definition now. Normal means at 1 atmosphere. And we had some data, some conversions, some equivalencies that were provided to us on our reading guide. Do you guys remember all the things that were equivalent pressure-wise to 1 atmosphere?
760.
Yep, 760 millimeters of mercury, Hg. There was one more.
760.
Okay, there's another one too. 760 torr and
760.
not 760 kilopascals. Look at my board here. What do you think? 101.3. All right, so these four numbers with their units are equivalent. Like 1 foot equals 12 inches. These things are working the same way. So when I say normal boiling point, or normal freezing point, or normal condensation point, it means the point at 1 atmosphere. So here's 1 atmosphere, which is 101.3 kilopascals. So what I'm looking for is the temperature at which this phase changes from solid to liquid. So if I'm looking from solid to liquid, that's this part of the graph versus this part of the graph. So it transverses those two pieces of the graph at this point. Well, the point is the temperature at which that occurs. So you read it by dropping your intercept down, and you'll note that the temperature at which this substance melts is what temperature? 0 degrees Celsius. And that makes sense for water, right? We know water melts at about 0 degrees Celsius. And the normal boiling point would be where we go from liquid to gas or vapor. And that's at 1 atmosphere. You're going to dot over here. Find the intercept between the liquid and vapor phase. Drop that point down, and you see that this is occurring at what? 100 degrees Celsius. And that's what we always quote as our melting points and our boiling points for water. But that's us assuming what? Atmospheric pressure. So 1 atmosphere or 101.3 kilopascals or blah, blah, blah. So what if I raise the pressure at which I'm talking about? Let's go up to like 2 atmospheres. What happens to, so where would 2 atmospheres be here? So this is 101.3. So where would what could I call it instead of 2 atmospheres? About what? About 202 kilopascals, right? So it's going to be way up here. Okay, so here, what happens to the boiling point? I mean, sorry, the melt, not that point, that's not the correct point. What happens to the solid to liquid, which would be the melting point right here? It goes what? It goes where? it goes just a little bit lower than 0. So at higher atmospheric pressures, the melting point is lower than 0. At higher atmospheric pressures for water, what happens to the boiling point? It goes a little higher. And that's the one that really makes sense, because that's where we just talked about the mountain example, or actually the sea, like Dead Sea. I already erased it. The Dead Sea example. Higher atmospheric pressures means below the ocean. The boiling point or temperature of that which it boils would be higher. So this graph gives us a lot of information about that. Quick labels though. What does D represent? Critical point. Good. What does B represent? Triple point. And what does every point from B to C? Every single point from B to C represent? B to C is here. Okay, every single point there is technically a melting point, but at different pressures. You could also call that solid liquid equilibrium. That basically means that you have solid and liquid existing together, which is the point at which something begins to melt. What's true using that same language for A to B? Okay, so that's going to be solid gas, what? Solid gas equilibrium, but what point would that be? Everything from B to C was a melting point. Everything here is a sublimation point, because that's our interchange between gas and solid. And then B to D, which is here. Say again? Liquid to gas equilibrium, and that's what point? Boiling point. We discussed the rest of those. We're fine for now. All right, so now we're going to go to heat curves. Give me a thumbs up on phase diagrams. You have a general idea of how to interpret. We're going to practice with a couple more examples. I just try to get most of us on board. I do want you to participate in the surveys, though. No, I think we're good on that one. All right, so here is your heat curve that you mentioned yesterday. On your heat curve you drew yesterday, do you have these labels on here?
Yeah.
Make sure they're all, I'm going to leave this here for a minute. Make sure they're all labeled. And actually, not this one. Make sure this is the label, because the other one's a little bit too in-depth for the time being. So make sure you have solid liquid equilibrium, liquid vapor equilibrium, and then if you have gas up there, that's fine. We generally use gas and vapor very interchangeably. They're not exactly the same thing, but we're going to call it tomato for now. Also put A, B, C, D on there, so we have some common language between us. All right, so what is not included here that was included on the phase diagram graph? Loud and proud, come on. Good, actually that's not a thing, but good, that's not here. What's included on the phase diagram but not on this one? Pressure. So this is assuming one particular pressure is applied. Okay, so on the phase diagram we got all kinds of pressures we can talk about. This one we talk about one pressure. Okay, so this is temperature in Celsius and then time. All right, so on this graph, which segments represent phase changes? Like which line segments represent phase changes? Say again? So give me like the letters associated. A to B and C to D, right? Those are the line segments that represent phase changes. What phase change is this one? But what is the title or what's the name of that phase change when you go from solid to liquid? Melting. And this one? Boiling or vaporization. Okay? And then we actually have an amount of energy applied here and here. They're different, but we'll get into that in our next unit. All right, so what we have to interpret is we know that melting is an endothermic or an exothermic process. Which one? Endo or exo. Think about the kinetic energy. Think about what's happening. Loud and proud. Okay, we're going from what kind of kinetic energy? Okay, what kind of kinetic energy for solid? Low kinetic energy to a higher kinetic energy, or medium, right? Kinetic energy for liquid. How do we get from low to medium? Add energy, right? So this is endo. So that endothermic process means energy is being exchanged, but what you're noticing is that what's happening to temperature here? What's happening to temperature here? It's staying the same. So temperature and energy are not the exact same things. Temperature is related to energy, but it's not the same thing. Same thing here. This is an endo process. Though we're like exchanging some energy here, it does not influence the temperature. So we're again going to mention temperature and kinetic energy are not the same thing. So what's happening to the temperature while the substance changes phase? Okay, so there's no change in temperature. And then what you should know, I don't have that on here. What you should know, and write this piece down because this is going to be related back to IMF's intermolecular forces. Okay, so as phase changes occur, say heat energy. Okay, so as phase changes occur, heat energy is used to overcome IMFs that hold molecules close together. And that means potential energy can change, not kinetic energy. And that's kind of the background, reading between the lines as you look at a heat curve, what you should be able to also interpret. So if we're talking about water, what IMF comes into play when we talk about water? So what intermolecular force holds water to water to water to water? All right. Okay, before you answer, quick review. What are the IMF types? There's 3. Ionic is the type of bond. Intermolecular force. Try again. There's hydrogen bonding. What else? Dipole, dipole, and London dispersion forces. Which one up here applies to nonpolar molecules? London dispersion would be applying to nonpolar. So these two apply to what? Polar molecules. And so water being a polar molecule, what holds it close together? And how does the hydrogen bond look when I draw it? Not H to another H. It's got to be an H from one attracted to the O of the other because opposites have to attract. That has a partial negative. That has a partial positive. I know, Throwback Tuesday, but it's way back there. You got to remember a little bit of stuff. Okay, can I go past heat curves? Yes or no?
Yeah.
For now, we're going to pass it. All right, so you guys have some practice we're going to accomplish first to make sure you are good to go on this. And then we're going to do one more thing together. So you can partner up. You're both writing on your papers, but this is your paper, so don't lose it. It's your lecture notes for this unit and this unit and probably like ending next week. So please begin as soon as you get this. This is yours to write on. So let's go ahead and all of us start on section 2. Which section? 2 and then go to 3, okay? So do sections 2 and 3 first. We'll go back to section 1 in a moment. If you want to work with somebody, you can move and work with them, but you don't have a lot of time. I'm giving you 10 minutes. 10 minutes. Quickly, come here. So, is the copy, the original copy. If you were out here yesterday, get a computer because you're doing something else first before you finish this. Ariel, testing. It won't take you terribly long. So Ariel, Nana, look up here for me. You guys see it Monday, classwork, phases of matter videos? That interactive? When you open it up, I want you guys to do the first. Sorry. Totally not even on the board. When you get to the link under homework from last night, or yeah, Monday, it says classwork, you're doing 1, 2, 3 videos, and you're actually going to draw the diagrams, label parts, write down details about anything you need to, okay? That's what we did yesterday in class, you guys do that first.
What's our structure that's going to actually melt down and become liquid as
So melting that's freezing.
All right, I only have a couple that I really want to check with you, and if you have more than that, let me know. So get booted up, go to my website, but pay attention as well, okay? So graph the temperature is number 1, okay? So who got to section 1? Not very many people. So write this down with me because I don't think very many people got there, okay? Graph temperature versus time for water going from solid liquid to, or from solid to gas, right? Make sure to label your axis and phase changes. There's actually another one I want to do, not that one. Number 3, graph temperature versus time of carbon dioxide going from gas to solid. So what phase change is that, gas to solid? Say again? Deposition, because solid to gas is what? Sublimation. But there's a, it says down the bottom, it sublimes at what temperature? Okay, so they're telling us the sublimation temperature, but what we know is just like the melting point is literally the same point as the freezing point. The sublimation point is the same as the what? Deposition point. The temperature is the same, it's just which way are we going? Are we going from solid to gas or gas to solid? So we're going from what here? What to what? Number 3. Gas to, so are we starting high or starting low on our heat curve? High. So we have to start with time on the bottom, temperature on the y-axis, and we're starting with the gas. So we're going to start with a slant up high, and that's gas. And then it gives us a phase change, and from there we're going straight to what? Solid. It doesn't intentionally say like skip liquid, but it tells us the sublimation point, which tells me I'm excluding the liquid phase. So what temperature does that occur? Negative 78.5. So this point right here is negative 78.5 degrees Celsius. And that's that point right there, that darkened port point there. And that, of course, is consistent to this point over here. So it's a horizontal zero slope line. And then I might even write like deposition here, so I know the process that's occurring. Okay, so essentially, if you can do that one, you probably should be able to do the rest of those. Are there any questions on section 2? I'll ask before I move past it. All right, heat curves are pretty easy peasy. What did you notice was different about this heat curve than the one I have structured here? Okay, so this one goes down, this one goes up, so there's a heat curve and a cool curve. What else? Right, so we actually can label these a little differently. Temperature is going to remain an axis, or the y-axis, but this can be heat added, kinetic energy added, or time. So there's a couple different labels you'll see. Don't let that confuse you. It's still a heat curve. It's just delineated with slightly different variables. All right, and then who's on my website? All right, go ahead and get on my website if you're not there. I'm just trying to answer a couple more questions here with you. All right, eyes back up here for me. On this question 4, they like to ask questions like this as like a multiple choice on your final exam. So this is a good one to make sure you're comfortable with. If I have if I had a quantity of substance at a pressure of 1.25, okay, 1.25 and 300 degrees Celsius, what state of matter am I at that intersection? Okay, so 1.25, and then you're going to look at 300. So about right there, right? So you put point there to say that's my initial starting point they suggested. And then it says you lower the pressure to 0.25 atmospheres. So does it say you change the temperature? No, so you're dropping from 1.25 all the way down to here, which is where the 0.25 exists. So we transition from what to what? Liquid to gas. So what phase changes that? Vaporization, boiling, something like that. Okay, so they like to ask questions like that. So if you feel good about that, give me a thumbs up. All right, so it's just plotting points in a graph and interpreting the transitions that are occurring. Okay, so now that you're on my website, let's practice this one more time. And this is a link under classwork for today, Tuesday phase diagram practice. So take a couple minutes here, and you should be able to get most of those. I think it randomizes it, so you may not be able to work together, so look for yourself right now. hoping deep down somebody actually liked that song. It was chemically just wonderful. I thought it was great.